to be here, and I hope everybody's having a great day today. We're going to talk about infrared thermography mostly, and I have some video, and we'll have a little bit of fun. But thank you to the Electricity Forum, and I like the workplace arc flash electrical safety mantra. This is just the abstract for it. Today I'm wearing a tie, but yesterday we were inspecting a fluidized bed incinerator at a wastewater treatment plant. Don't need a tie for that. Infrared applications are many. There are a myriad of things that you can do, just basically your imagination. Everything has to do with the energy and being able to see that energy with the infrared cameras. This is a kind of a list of services that are offered in North America. And as you can see, electrical switchgear testing is the #1 use of infrared thermography. Absolutely the #1 application. Trick is the thermographer needs to know what he's doing, needs to know what, safety and get the job done. And there's some technical technical things that you need to know what to do. We will get back to this, but this picture here, but as you can see, the cold conductor in this case, it's so loose that you would think, looking at infrared, kind of thinking about it, oh, the hot one's loose, but in this case, it's not. The cold one is the problem. A little, just light background. Look, you guys are, Randy told me yesterday that you guys are going to receive a PDF of this presentation and a link, I guess, to watch it. So that's great. And so we don't have to go over everything that I've got on everything, but basically the electromagnetic spectrum, where we're looking at is just below visible light. So you turn on the stove and it gets red, then yeah, you're getting into infrared. And thermal infrared is really categorized into 3 kind of groups. First law of thermodynamics, we don't need to discuss, but just understand that higher energy goes to lower energy because the universe kind of wants to equalize. And that's really everything. When you've got convection, conduction, and radiation, and you put an infrared camera where the radiation's hitting it, and the detector basically turns into a way to make a video picture. And these are the different detector methods. We're stuck in uncooled microbolometers right now, but there are photodiodes and photo transistors, and as the prices become less and less and less, more and more people will use infrared. And we'll talk about that later. I started in the 80s, and we lugged these big giant cameras around with these carts, and it was clunky. Everything was clunky. Now, and you got a cell phone. Here's the winner of the oldest image that we could find anywhere by Gary Orloff, Bernie Lyon, and Dr. Bob Maddig. This is a motor, an automobile engine from 1960. There is a myriad of cameras. There's lots of different cameras. It's an electronics business, so that's the way it goes. There's competition. FLIR Systems is Teledyne FLIR now, and they make really good equipment, and they have this is the kind of the way they do it. They have series of cameras, so they have different form factors where you got like cell phone, very light handheld, compact, light handheld, and I'll call it heavy handheld, but they're not that heavy. Compared to the cameras we used to lug around, they're feathers. And I threw a couple of ads in this presentation. I hope you don't mind. United Infrared is a company that sells infrared equipment. We're dealers for all these camera manufacturers. We do infrared training, contractor support, client services, that kind of thing. Yep, we got a store. Click on it. Peter Hopkins knows every feature of every camera on the planet. And I want to talk about this a little bit later too, in a little more detail, but we're having a conference in a couple of weeks in September here at Lake Tahoe, and I want to invite you guys to come. Back to the cameras, there is some technical specs that you need to face. As far as the detector themselves, the type of detector, wavelength, the sensitivity of it, which, but these days, almost all the cameras are good enough sensitivity, and the spatial resolution. Now, spatial resolution, that's what you're basically buying. But all these factors here, portability, expandability, electronics, ruggedness, ergonomics, this is stuff that you cannot know and buy over the internet. You need to put your hands on these cameras before you decide to get one. You need to put your hand on the camera and play with it, see how you like it, see how the electronics work, see how the buttons work, all that kind of stuff. On the sensitivity, it's just basically, can you discern the difference in temperature? Is the detector sensitive enough to see something? And I can tell you, the farther away that you can get from the object while maintaining enough spatial resolution, pixels, the better off you are, because you get the big picture. The big picture is what you want. These are like 3 different sets of widths and heights of pixel setups. So that there is some degradation from putting lenses and filters and things like that on, but it's kind of insignificant. But basically, the higher quality image will give you more pixels per inch. Again, you're buying pixels. So when you're contemplating buying an infrared camera, think of everything and play with the camera and actually try them out. When it comes to the electrical infrared predictive maintenance, it's not preventive. There's nothing preventive. It's predicting that something's going to fail. You have annealing. You have a lot of times this curve is not actually perfect. It bounces around. You may have some connection get really hot. It could anneal itself, make a really good connection, and then cool off. But it eventually, it's going to fail. And the people that figure out, the algorithms for the cameras and the thermodynamics and all that stuff, those are scientists like Bob Madding here, probably the most famous thermographer in the world. Dr. Bob, love you, brother. And I want to show you guys some examples of what thermography looks like. Just a photo and an infrared, and there's a little description down below there. And again, you're going to get this PDF, so you don't have to go over every single picture and talk about everything, but I just want to kind of take a few minutes. Again, far away, great. If you can see what you got to see. may have to get down and on the ground and find these problems, but you can fly transmission lines. People use helicopters to do it. They're doing it with drones now. It's the same principle no matter what, I squared R. Whenever you have heat, you have excess heat, it's gonna be hotter than the thing beside it. And these are just examples of different components as they heat up. Most of the time, the connections themselves fail because they either vibrate loose, they corrode, there's lots of ways they can fail, but they also can have mechanical problems like these bushings not being tightened up. And there's always well, at the factory, it was Friday afternoon and we forgot to put these bolts on with the Belleville washers on there. 900 degrees is almost visible light. Again, just samples. This is actually induction heating. Bus ducts were one of the first uses for infrared thermography because the manufacturers that were selling the bus ducts could not get it past the chief engineer, the electrical engineer at the plant, that they had that much space in between all this power. They had that much space and it wasn't going to explode. So they kind of used it as a sales tool. And again, there's very, very similar and common things that you see. Loose lugs on breakers, bad fuses, fuse clips, switches, knives, pivots. These all things electrical fail because of resistance eventually. There's that picture we saw before. Again, the cold is actually the loose lug. And these things go on meltdown. I mean, you can visually see damage on lots of things that, a lot of times, we'd be scanning panels over the years, find something, and as you look at it close enough with your eyeball, you can tell that it's got damage on it. And I'm going down, into smaller and smaller equipment here. Eventually, we'll get to a microcircuit. But these are the kind of things you see. Actually, the breakers themselves can have failure, be ill-designed or ill-maintained. Something can go wrong. Probably the most common, if you took all the millions of things that get found every year by infrared cameras and switchgear in every building, tons of buildings in the United States and Canada and everywhere. These fuse clips, these types of fuse clips are probably the most common. And of course, breaker lugs and wires loose. When you run a circuit too warm, it's going to heat the breaker up. And you can tell when you're looking at an infrared image of a panel, yes, you can use one of these, but this thing is going to measure a very, very tiny little spot. It's hard to actually put it on the right spot. An infrared camera is much easier. I'll do a race. You use this, and I'll use my camera. So when you see something like this, load is very, very important to this. You have to load the circuits. You just have to load everything because you can't do this with no power on. Again, common problems, and sometimes you got just bad fuses, and we got broken stuff. So, just going through the different scenarios, these can be really bad here because the bus connection loose. nobody will really see this. I'm going to talk about this in just a second, but you have to take these covers off. You can't shoot through the covers. And the mercury switch, confounded things, they're all probably electronic these days. And, you know, DC works the same. As we get smaller and smaller into this, you can see that nothing changes. Same thing. It's the same exact thing. You have loose connections. You have a little heat. There you can see a little burn mark here. Right there. And again, just like with the 500,000 volt lines running across from Venezuela to Colombia, from Guri, they have failures on the lines, and it's all the same as that microcircuit right there. All right, so now let's talk about the arc flash and how the electrical safety in general, things like that, and how what infrared actually does. You know, condition-based maintenance is the way to go with the switchgear, and this is SOP now. This is completely SOP. The risk managers have figured out that infrared, if they put pressure on the owner of the building to do an infrared survey, they're going to get it done. And it also, you know, of course, just in general helps promote safety. And you're decreasing the risk because you're doing it on a frequency. Now, I know some codes might say 1 year, 2 year, but it doesn't really matter. When you go in and do a survey, you assess what you found in the place at that moment. And there's a lot of things you need to think about, especially with loading. Loading is very important because if you go in the summertime, you're not going to check the heat strips and the air condition and the heating system, and vice versa. So the way the loads move around is critical to this thing, and that's the way it works. So you figure out what the operation is, you figure out when the best time to do things, when it makes the most sense, come back and you recheck things as you can. Again, the predication for this whole thing is that you get heat from resistance. With mechanical, I mean, it's just friction. You go like that, you can feel it. Again, electrical infrared is a completely integrated program now. All the insurance companies recognize this and are doing a lot of they either reduce your they'll either up your rate or they'll give you pressure somehow. If you don't do it, they'll maybe make your deductible higher or something. So good thing about doing infrared on switchgear, reduces the downtime risk, increase the life, lower the risk in general, more profit, save on insurance maybe, prevent catastrophic failures, lowers the cost, increases everything. I said profit twice. And if you're kind of smart about it, you can do arc flash surveys and infrared at the same time. You got the stuff apart anyway. You need to measure loads and that kind of thing. You're following down the one-line diagrams as you go down. So it's not a bad idea. Now, let's talk about increase of risk. Yes, I hate to say it, but it's true. It is a fact of life. When you're removing and replacing panels, especially when they're under load, if you can, there's lots of ways to mitigate risk. And it's not a bad idea to mitigate risk. But there is an increase in risk from doing an infrared. You know, if you leave it be, you're not doing anything, your risk is lower. So you, and again, the panels, read this and heed it. The panels have to be removed. But who wouldn't be willing to pay a little bit more, take a little bit more time, plan it out better, and get a proper job done? So should an IR survey of any building be carried out without removing the panel covers or looking through windows? Absolutely not. In the future, as far as monitoring switchgear, there will be a time when, you know, everything's got an IP address, and you've got little teeny tiny cameras that are put in the switchgear and manufactured in the OEM, everything in it, and that'll be great. And it'll probably take, you know, 20 more years or something like that. In the meantime, there's, you know, kind of a little thing. You got the guy going out like we do, go out, shoot the switchgear, make a report, tell people what to do. They go out and fix it before it fails. In the meantime, there's infrared windows. Iris is a company down in Florida, and they're a great example of making infrared windows, and also this Delta T system they call it, basically a wireless system that you put on a monitor. I got a couple of slides on that, but basically, infrared window has got a high transmission rate in the infrared, so you can kind of see through it. Not perfectly. You got to be able to calculate it. Again, you need to be competent to do this work, but it's doable. And this is a lot easier than taking all this stuff apart while you're working. I really love these windows. They make life easier. You can read all this, but it's just the case for putting in IR windows. And the wireless Delta T, they call it. Basically, you know, it's kind of monitoring the whole thing, and then it sends a signals alert. Like I said, eventually that's what's going to happen. So that's kind of thermography. You go out, you make reports. They're beautiful. You send them to people. They go fix the stuff. The world's happier place. And you know, as part of this presentation, I thought I'd show something. Now, a couple things about this. Basically, this was done when these people where manufacturers were just starting to, in 2000, I think it was 2006 or 7, when we did this. I did not go myself, but Ron Predmeski went from our company, and basically set up this test where we're looking at the suppressive quality of SF6 gas versus, you know, nothing. So in this case, I'll just put the slide in just to say something, but 80% of the SF6 produced worldwide is produced for the power industry. And of course, they're trying to fade it out. It's greenhouse. Again, the concept here is we're only worried about the first 15 feet, which is roughly right in here. I'll show you a picture. So this is about 15 feet. This doorway here for reference. The fire shoots out, stuff comes out, and the test setup is, you know, just looking down this way. It's a really nice high-speed infrared camera called the Phoenix midwave. And you attach to one side and the other on this test kit, and then this diaphragm shoots out the stuff. I mean, what could be more fun than blowing up things? So the test setup's basically this, and I'm going to just show these. These are, I do have the high quality videos, and Randy, you tell me if we got time to show the super high quality, but this gives you a good idea. These are just embedded in here. And I'm just going to play this over, and look, this happens faster than this video. So watch, click, bam, just like that. That's how fast it happens. All right, so that's the SF6. All right, and then here's the air. So I mean, you can already tell it's already more violent, spewing things. And I got a couple of slides to compare. I'll show you, but I looked it up on Wikipedia, and then I went to the true wonderful source of arc flash and electrical safety, to the electricity forum, and I saw a bunch of, wow, it's just full of information, just full of it. So this is, you guys are on the right place here. I put a link down here. But components of an electrical explosion: heat, radiation, pressure wave. All right, so the first one, the heat radiation, 35,000 degrees. Holy cow, that's really hot. And it is absolutely above the capability of any infrared camera ever made, period. And probably will never, nobody will ever produce one like it, a measure. And these explosive pressure wave is again interesting. But we weren't so much concerned with the pressure wave, but I'll show you what we did see. So we've got these two things. Here's what we found, and I'll show you some still pictures. This is the order of the event. So first you get radiation, bam. Then you get flame. Then you get shrapnel with the flame. Then you get a pressure wave. Then the flame goes away and more shrapnel shoots out. And what was interesting in this, now we're not doing an ASTM test here. There's too many goofy factors that nobody wanted to, and we didn't need to worry about. We were just saying in that box, how much, what would the reaction of setting this off in SF6 gas as compared to air, and that's what we were doing. So what we found was a lot more flame area, higher flame temperatures, much higher. But we got about the same flame travel, and we got more shrapnel. So this is, if you look on the left, this is I would call it test 1 is the SF6, and test 3 here is, a relative comparison of frames. So as you can see, the flame temperature over here and by the way, this event, as I said, it goes pretty fast. Those are, thousands of seconds. So this says 1299 C, pretty hot. So you got compared to 2000 plus over here on the air, same thing here. So I'll just flip it back and forth for a second. And then you get that spew of the chunks. So if you just flip it back and forth, you can see kind of how the event looks. The air is much more violent. The shoots out a lot more stuff. the flame goes about, actually, like I said, the travel's, you know, almost the same, but it's, as you can see, it's a lot less, it's a lot more streamlined, and giant chunks of, you know, pieces of copper flying all over the place. A lot more with the air. You know, it's like you need the bomb suit. And there's the temperatures, all the temperatures are way higher. So, and then they did a couple more tests, and I'll show you, this is mainly just to show you the pressure wave thing. They lined this thing up with this and shot, you know, like straight into the guy's heart. That was the idea there. And so here's that. Again, you know, this is a kind of low quality video. You still see it, boom, just like that. I can stop this kind of, sort of. So I'm going to just play it a little bit in advance and just show. There you go. You can start to see now. Bam. Now look at the seconds here. So the whole event takes 1.1 second. And there's, you know, a lot of frames. So as you can see, this is kind of a straight line here, although it gets ugly in a minute. But and you can also see where it lights them up when the heat energy hits them, and then they start, you know, it starts going, you know, rest in peace kind of thing. So anyway, that's that. And again, you can play, you can play this video. You can tell. I can play, like I said, I've got them sitting right here. I want to do this. These are just a couple of slides from it. So, and you can see over here the flame travel and the temperature. Whenever you see this checkerboard pattern, that means that it exceeded our setting on the camera. Whenever you see that in infrared, it's blooming. Well, it depends on the type of detector that you're using, but you've exceeded the camera's ability to measure in that set of range of temperatures. You can adjust those, but anyway, it whacked him pretty good right in the heart. You know, they build these, we're doing this thermal imaging conference where we have an electrical track, and ICI has this long wave QIP camera here, which does, there you go, sulfur hexafluoride. So you can take an infrared camera and go to your substations and look and see if they're leaking. Looks kind of, it's like, you can see it looks like smoke because it absorbs everything except that wave. The fellow that owns the company is Gary Strahan, pretty famous infrared guy around the world. And he's going to be in person for a day and a half at the thermal imaging conference. Again, the track is track 4. The conference has got, you know, things for drone people, home inspectors, thermographers that do stuff like fluidized bed, incinerators, you know, process control, that kind of thing, flat roofs, and all those other myriad of stuff that you do. But the electrical, if you're an electrical contractor, you know, this could really be a good thing for your business. You got 2 weeks. If you want to come, you can send your guys. It's not a bad joint. It's the Bally's Resort and Casino in Lake Tahoe. So pretty nice place. And it's a live event, you know, pandemic. Oof. Anyway, this is a live event, so everybody's going to actually be there. You put your hands on the cameras. You can talk to people that do this stuff for a living. You get specifications. this is a little outline of the course. It runs over 2 days, and then because of the electricity forum and doing this, we made a thing where you could go to all 4 days of the conference, and it doesn't cost anything more. So it's $595. Co-workers are $500. Spouse rate, we lose on that because they'll eat more than $250 worth of food. Anyway, thank you for your kind attention. And if you got any questions, that I put this notice on it because I don't want, don't steal the images and use them on your website. But you're more than welcome to review this, have fun with it, and I'm sending Randy a PDF of this presentation, and he'll also have the
okay, great. Thanks.
Video, I guess.
Thanks very much, Greg. That's great presentation. Okay, a couple of questions. Can infrared really tell us when there will be an arc flash condition?
It can tell you after it happens, but no, it's not going to predict. It's predictive maintenance. Yeah, remember Dr. Bob's curve. It's going to, eventually it will fail, but you can't look at something with an infrared camera and know the moment before it explodes. There's no event that could happen. And besides, what good would it do you? It would be that moment would be so quick that you wouldn't be able to get out of the way anyway.
Okay. The next question, can the light reflection change the temperature values shown by the camera?
Well, that's why we teach these courses. There's a little physics here. I had to tell you, it's a little bit more than high school physics, but it's not bad. The way thermography works is you get certified. There's several outfits that have a good example is Infraspection Institute. They publish standards. They have training classes. We resell on UnitedInfrared.com. We resell their training classes and things like that. But to answer the question, there's we call it in here reflecting on emissivity. There's issues with measuring temperatures. You have to learn what criteria to use. You have to learn how to measure temperature. I hate to tell you, but the infrared cameras are not very perfect measures of temperature. And you're not touching it. It's better to take something, put it on a thermometer, and that's very, very accurate. There's a lot more accurate ways, but you don't have to touch it with infrared, and that's the whole trick to it. But you need to know how to, adjust so that you're getting a correct temperature. And that's the purpose of the training. It starts off with, basically qualitative. That's, seeing the difference between something that's wet because of, and what the reason is. It's wet because you have, it looks cold because it is wet because it's evaporate. It's evaporative cooling. With this, you're looking at differences in temperature because of friction or resistance. Every kind of subcategory of thing you do with an infrared camera, you have to learn some tricks. Just like plumbing and everything else, there's tricks to it. But qualitative is level 2. So level 1 is quantitative or qualitative. Level 2 is quantitative thermography. Level 3 is about program development, not unlike arc flash surveys and coordinating things in that, the same way, setting up programs, certifying your thermographers, and that kind of thing.
Right. Okay. Final question. What is the minimal distance to make the measurement with the camera in an electrical connection in an electrical panel? What's the minimum distance?
Okay, so again, now we're talking about what's called spot size to target distance ratio. So if I use this little gun, and it just because it shoots out a laser that might make a little red dot, that doesn't mean that it's measuring the temperature there. It's like, actually, there's a cone on here. I don't know if you can see that. There's a cone on it.
Right.
Well, what happens is, first it pinches and then it gets bigger. So it starts out, it pinches, then it gets bigger. So if I put my hand here and the target's that big, I'm getting all this air over here. So if you want to know the highest temperature, the way you do it with these is you just put the thing in a mode that finds the hottest temperature and you just wave it around a lot. With an infrared camera, it'll go to it. But I can, let's talk practical stuff.
Mm-hmm.
You're 4 feet away, 4 or 5 feet away from a panel. You've got a 320 by 240 camera. You're getting plenty good enough resolution, spatial resolution to be able to measure the high temperature. Let's talk about, this is practical stuff. We're not doing a scientific experiment where we're trying to measure 1 pixel. But so if the answer to the question is, I would say maybe 3 feet with a 320 and 4 feet with a 640 camera. All right, thank you.